Hello, I am Gunnar Tufte. The work I'm presenting was done together with Johannes Jensen here at NTNU. It is in the area of material computation, exploiting the emergence and self-organization in nanosystems for new novel computational systems. The system we are interested in are complex dynamical system with large amount of simple units, capable of displaying emergent at the global observable level. To measure and quantify computational property, such as information exchange, information processing, and memory, we place our nanosystem in the Reservoir computing framework. We investigate tunability, that is finding parameters that enable computational properties. And even more interesting question, does an artificial spin ice based system have the possibility to scale? Artificial spin ice are very promising system for computing. They have a lot of the required features. Artificial spin ice are magnetic system. They are used a lot in experimental physics. It is a regular grid with nanomagnets, organized in some repeated patterns or geometry. This makes an ensemble of nanomagnets, here seen as rectangular or stadium-shaped magnets. The interaction is based on local magnetic fields in the nearest neighborhood. The magnet's length and thickness can be set to make the magnets act as dipoles or spins that can only toggle between two directions. This property enables us to treat the magnets as binary toggling units. Physical artificial spin ice can be produced. The image here is from our nano lab. The state can be read out by magnetic force microscope, as shown here. Further, it is also possible to model the system at a very low level by micromagnetic simulation. However, such an approach requires a lot of computational power. Ensembles of max 100 nanomagnets can be simulated. However, if the magnets are modeled at a higher abstraction level as dipoles, it is possible to model large system with millions of magnets. That is the approach we have taken in this paper. This is about computation. To make that happen, we need inputs and outputs. For inputs, we can use external magnetic field to perturbate the system. The input can, for instance, be represented as amplitude modulation or a change of angle to represent the bits in an input stream. We have chosen the latest approach in our paper. The behavior and emergent property in artificial spin ice are highly tunable. By changing the geometry from square on the left to a pinwheel-like structure on the right, the dynamics observable change from wave-like patterns in the square to large spatial patterns for pinwheel. The behavior can further be tuned, for instance, by changing the distance between the magnets, tuning the shown alpha parameter. That will also tune the coupling strength and information exchange between magnets. So how can artificial spin ice be used as a computing substrate? We use it as a dynamical system in a reservoir computing framework. The artificial spin ice is a dynamic system that transforms inputs to a set of high-dimensional outputs. The framework enables us to use well-known metrics from reservoir computing to explore possible computational capacity in our system. We measure kernel quality, giving us a measurement of how good the system is to separate data, and generalization to measure the degree of finding similarities. Since both are needed, we also calculate the computational capacity Q out of these two measurements. The spin ice we use has a pinwheel geometry. We use the fixed number of magnets, 220. We encode input data as a stream of bits represented by the angle of an external field. The strength of the field is constant within one experiment. The simulations using a dipole-based simulator called flat spin. In our experiment, we use bit strings of length 100. For the kernel metric, 220 random generated bit string are used. For generalization, also 100 bits. However, the first 40 bits are random and the following 60 are equal, enabling us to observe if the reservoir has fading memory. The details on the artificial spin ice is also shown. Note that to introduce some kind of robustness, we have used 30 slightly different systems to compensate for production defects. As such, all our K and G values are average over 30 systems. So, in our first set of experiments, we investigate the influence of the local interaction between the magnets, alpha, together with the influence of the magnitude of the external field, H. We do a parameter sweep to generate heat maps for kernel and generalization measurement and calculate the computational capacity. The plot clearly show that there exist spots where the coupling strength and the external field magnitudes match as to provide computation for all three parameters measured. In the plot shown here, kernel, generalization, and computational capacity along the ridge line of each heat map is plotted as a function of the coupling strength alpha. The plot clearly shows that too low coupling or too strong field will enable the current input to dominate the system. No memory is preserved. Further, the resulting Q show areas where the dynamics is tuned to support good measurement for both kernel and generalization. Not too chaotic, but still with enough information flow to support fading memory. So, the big one, can our system scale? In a way, a requirement if we want to have realistic computation. We need to have some form of parameter to scale the system. To get knowledge of scaling, we look at a fixed system, that is a fixed number of nanomagnets, 220. We have a constant state space, or a reservoir can be seen as a number of nodes. With 220 magnets, we can read out 220 signal at max. Each node can be a binary number, a single spin. So what we scale is the node size. That is the number of magnet within a node Here we illustrate this by nodes with 1, 4, and 12 magnets. As such, we scale what a single node can express. As shown in the example, with 4 magnets, we get a grid of 7 by 7 cells. The readout from each cell can now be represented by a vector with magnetization direction and magnitude. We scale from binary output nodes, single spin system, to system with fewer nodes with enhanced expressibility. Such scaling is extremely important if we want to go beyond a theoretical system. A system where scaling depends on increasing the number of inputs and outputs do not scale. It is impossible to scale up to thousands or millions of readout probes in the system. So then, are we able to retain computation within this scaling scheme? I say retain here since we do not actually scale computational power. The underlying system, 220 magnets, is constant. For the scaling experiment, we do the same exercise as for the first experiment to find good parameter for coupling strength and the external field strength. However, now we use a baseline of a 5 by 5 grid as node size when we sweep the parameter space. As can be seen from the heat maps, we get ridges of good parameters for K, G, and Q, implying we have the necessary dynamics for kernel quality and generalization. Note, since our metric depends on number of nodes, the results are here normalized. The plot shows the scaling of performance for the system as we scale the number of nodes available and also what's in the node. And yes, we are able to get good performance in the system. However, even more important, we can scale the number of nodes up and down without that much of a loss in performance. An interesting observation is that the system is best around 5 by 5, the system used to pick H and alpha parameter. However, the system is able to perform when the node size increases and the number of readouts are reduced. The dynamics in the system still provides information processing and memory. Note, we do not optimize for each grid size. We keep one set of parameters for H and alpha to measure the presence of scalability. And the optimization of H and alpha for each grid size give better metrics performance, but do not provide the single scaling factor in node number we need to compare results. So to conclude, artificial spin ice show excellent computing capacity. The dynamics can be tuned to perform well on well-established reservoir quality measurements. We have evidence of fading memory, the important echo state property, computational capacity when scaling is achievable. We show that we can scale the capacity in nodes and still maintain good performance. That gives us a possibility for physical system with a practical number of inputs and outputs. Computational capacity is tunable and possible at different abstraction levels. At the small scale dynamics of simple spins and with large scale spatial patterns of metamaterial. At the end, I would just like to point you towards our simulator flat spin and hope more people are interested in looking into artificial spin ice and looking into the use in unconventional computation and artificial life. It's a fun and great substrate. Thank you very much.